Okay, here we go. So let's start with this example. All right, so I have a vector field here, minus y over x squared plus y squared, x over x squared plus y squared, and the notation we'll use is that the x component of a two-dimensional vector field will be capital P, and the y component of a two-dimensional vector field will be capital Q. That'll be the convention that we use. And then if we have a third dimension, it will be R. R will be the z component of a three-dimensional vector field. So, is it conservative? How can we? What's the fastest way to find out if this is a conservative vector field? Yeah, Andrew. Right. We want to compare what p, the rate of change of the partial derivative of p with respect to y, and the partial derivative of q with respect to x. Now we're not going to take the time to do that, so we're going to compare those two. You can do quotient rule or you can do product rule. I'm showing here product rule. Don't try to write all that down. But the moral of the story is q of x is y squared minus x squared over the denominator squared. Py is y squared minus x squared over the denominator squared. Conclusion? Conservative. We got those partial derivatives are the same. And that was kind of like back, we talked about something called Clause's theorem. Fxy equals fyx. Second derivatives are equal, right? Second derivatives cross partials are equal. And so then I'm showing the field, the little purple arrows, very small, and I've got two circulation loops. I've got the blue square and the red circle. So what do we predict for these circulation intervals? The path of the blue square and the path of the red circle. What do we predict? Okay, conservative vector field means that every closed loop will result in zero circulation or zero work if it's a force field, right? And so here's the blue square. The blue square, the first I traversed around this way. Here's C1, and actually that along there is 0, and then C2 is up this side here. And I got some weird decimal, 0.46, and then across over here is the third one, 0.3218, and then down the fourth side was negative 0.7854, and I added all those up, 0 plus C2 plus C3 plus C4, and I got 0. Right, so I did f dot dr each time. F dot dr, which would be p times dx dt plus q times dy dt, etc. And I added all those up, and I got 0. Okay, so let's do this ourselves. Okay, let's do this one ourselves. So it's the unit circle. So how do we parameterize? What's the parameterization of the unit circle? Cosine t, sine t, right? All right, and then we're going to do f, which means what? PQ dot dr, right? dr. And t represents what quantity in this case? Angle measure, right? And so we're going to go from what to what? We're going to go from 0 to 2 pi. And without writing everything down, can we see what happens here? I'm going to have my p is going to be what? Negative sine over what? Cosine. Do you see this? Cosine squared plus sine squared is the denominator. So I'm gonna get 1, right? See that? And then same thing. So now we're gonna have what? Cosine over 1 again. That's nice. And then what's my dr? So derivative, negative sine t, and cosine t. Have I made any mistakes yet? Dot product, negative sine times negative sine is? Right? Cosine t times cosine t. Equals integral 1 dt equals 0, right? Uh-oh. What does that equal? 2 pi. Did we do the math right? We did do all the math right. I can show you I can show it to you on GC. We did the math right, and we got 2 pi. Any questions on that line integral that we did? So I did P and Q evaluated at R, right? I plugged my X and Y of R into my P and Q. Dot dr, and I ended up getting just the integral of dt from 0 to pi, which is 2 pi. So something's wrong here. Something's up, right? We know that in a conservative vector field, every closed loop should give us 0 circulation, right? Should give us 0 for that integral. Okay. So I'm going to keep you in suspense. We're going to pause this. and we're going to talk about Green's theorem, and we're going to come back to it. Okay. So there's a mystery here. There's a mystery. What's going on, right? What's going on? This doesn't jive with what we said before. Okay, so Green's theorem. So put that aside, put that on the shelf for a second. Green's theorem, here we go. Suppose C is a simple means doesn't cross itself. Closed means makes a loop. Curve, so it's a simple closed curve surrounding a region D in the plane and oriented so that the region is on the left as we traverse the curve. So let me draw that. See if you can abbreviate that. Don't try to write every word. It's going to take too long. So here's a simple closed curve. It doesn't cross itself. It makes a loop. And we want that oriented. I mean, there's two ways to go, right? We can go clockwise or counterclockwise. And we want the orientation to be so that if we were walking on it, the interior of the region would be on our left. Our left. So would that be walking counterclockwise or clockwise? You should see that I would be walking, what? Counterclockwise. So if I walk around counterclockwise on this loop, the interior, D, will be on the left. And then this is in a vector field, PQ. That's supposed to be a D. Okay, so then here is, given all that setup, here's Green's theorem. Green's theorem says that the work or the circulation around the boundary of D, or around C, is equal to the double integral over the region D of this function, Q of x minus Py. So the partial of Q with respect to x minus the partial of P with respect to y. Do those two things look familiar? The partial of Q with respect to x and the partial of P with respect to y? So how have we been thinking about those lately? What kind of thing has come up lately involving those? Checking if the field's conservative. When will it be conservative? If those are equal. And if those were equal, what would we get? 0. And if we were in a conservative vector field, what would the circulation around the loop be? So that makes sense, right? So it's Green's theorem is kind of like if you're in a conservative vector field, it's kind of trivial. Like it just everything turns to 0. So it's more interesting in a non-conservative vector field to use this, because in a conservative vector field, these will be equal, and so the left side will be 0 because it would be the double integral of 0. But then in a conservative vector field, we know that every loop gives 0. So it works for a conservative vector field, but it's kind of a trivial case. Does that make sense? Just 0 on the right and 0 on the left. They both make sense as 0 in conservative vector field. Okay, so what we want to investigate is, this is like a fundamental theorem. This is like the fundamental theorem of calculus, the one you said in Calc 1. So here's that. So I want you to take a minute and see if you can kind of see what you can match up here. See what you can see the parallels. There are 3 major parallels that I want to focus on in comparing this Green's theorem to the fundamental theorem, the basic one from Calc 1. So first of all is, can you match up the sides, right? So can you match up which side goes with which side, first of all? Is it right to right and left to left, or is it a crisscross in terms of matching up? And then what are the other elements here that are parallel to each other? So I want you to get up 1 or 2 people to talk with, just for a minute or two, and see if you can see the similarities, the parallels between these 2 equations. Go. Everybody's talking to. Okay. So here's the 3 things I want to focus on. The first thing is, in the fundamental theorem, we talk about the accumulation of lots of bits of change, right? The accumulation of lots of little bits. Okay, so on the bottom one, is that the left or the right side? The accumulation of lots of little bits. Left or right? That's the left side. What about the top? Left or right? Accumulation of lots of little bits. It's actually both, but which one of the sides, left or right, is going to be parallel or kind of go along with the left side on the bottom one? The rights have it. Okay? So we got the accumulation of many bits of a quantity. Accumulation of many bits of a quantity. We want to think of that in Green's theorem as our double integral, and we're going to talk about that in a second. We know in Calc 1 that that's the integral side, right? And how is each little bit calculated? Each little bit is calculated how? Yeah, rate times little change in whatever independent is, right? So and this is what I'm underlining in purple. So you have the rate of change of f times a little change in x. Is parallel to, or is like, see, these are derivatives, right? So this is something of a rate of change. This is something of a rate of change times a little change in our independent quantity. But now in a double integral, a little change in independent is like a little area, not a little change in x. And what is that equal to? So when you sum up the accumulation of lots of little bits, what do you get? Charlie. The net change, right? The overall change, the total change, or the net change. Okay, and so what we see is that's these sides. So the net change of the quantity, and that's associated with the boundary. So like here it was the final value, the final value of the quantity minus the initial value of the quantity. So all you have to do is look at the boundaries of the interval, right? You look at the function value at the end minus the function value at the beginning. And that's kind of analogous to what the boundary of our region. So if we do the circulation integral around our region, that's just focusing on the boundary, right? And so the net change around the boundary is the same as the accumulation of bits of change throughout the region. That's what Green's theorem says. So the colors don't show up as well on this screen, but just trying to give you this. So these are the 3 main things I want to focus on. That you've got the accumulation of many bits. That would be the double integral in Green's theorem and the single integral in the fundamental theorem. And each one of those bits is calculated as something of a rate of change, times a little change in your independent variable. And what's that equal to? That's equal to the overall change, the net change associated with the boundary. If it's an interval, it's associated with what? The endpoints of the interval. All you need is the end and the beginning. And you did a lot of that with the fundamental theorem of line integrals, right? The fundamental theorem of line integrals is very, very similar to this, right? But the net change of the boundary of a region would then be the integral around the boundary, not considering the inside anymore. Okay, does it make sense? All right, so let's dissect this a little bit more here. I'm not going to actually write out the proof, but I do want to talk about it. So what we do, so looking at this first picture over here in Green's theorem, is we chop this thing up into a bunch of little elements. And what we're going to do is we're going to sum up, we're going to do a little loop integral on each element. So we're going to do a little loop integral on that, little loop integral on that. So every element, we're going to do a little circulation integral. We're going to break it up into 4 pieces, and we're going to do a line integral around each one of those, okay? And that takes us in 2 different directions, okay? The first different direction is what happens when we do that. So look at any 2 that are adjacent, what happens? We're going to do the integral as we come around this side. We're going to be adding up these 4, and we're going to add up this one going this way, but then we're going to come on this element, and we're going to add that side going this way. What's going to happen? Those are going to cancel out. And that's going to happen for every shared side of 2 little elements. All those are, as we calculate every single circulation integral, line integral around those, every shared side is going to cancel out, leaving what? So what doesn't get canceled out? What's left? All the ones on the boundary aren't a shared side, right? So all the ones inside are shared, but all the little sides along here are not shared, and those are left. So all the shared side of elements sum to 0, leaving only the sum around the boundary. So that's our circulation integral side of Green's theorem. So the picture here is that one, and so this thing, like that. Okay, now the other side is harder. The other side is harder, but we can do it. So now we're going to focus on what is the circulation of one element, regardless of the fact that we get cancellations. What is the circulation for one element, and what's really going on with that? Okay, so here I've drawn one element at x naught, y naught. And then there's the vector from the vector field associated maybe with the center of that, okay? And so that would have components what? P naught and Q naught, right? So P naught would be the x component of that vector. I made it too long. And then Q naught would be the y component of the vector, right? No, no. Yeah, right. P is the horizontal component of that vector, and Q is the... So when we're doing C1 and C3, all we're going to care about is what? In terms of doing the line integral for C1 and C3. All that's going to matter is P, right? P. So the P, or the x component of F naught, is the only thing that's going to play into when we do the line integral along those, parallel to P. Q is perpendicular, so it'll have no contribution to C1 and C3. Does that make sense? Okay, so we're going to sum up C1 and C3. And it's only going to have to do with P. So these are P's now. So when we add those 2 sides up, notice we're going in the positive direction here and the negative direction here. So we're going to get P dx this way and negative P dx this way. So we're going to what? We're going to integrate just along that little edge as be positive for C1, but negative for C3 because we're going the other way. Just look at the video later. Yeah. Just look at the video. Yeah, we don't have time. Sorry. All right, and so then what is this then? If you notice then, this is how much P changes with respect to Y, right? So we have a change in Y from here to here. So when we take the difference of this P minus this P, we're really looking at how much that amount of, you know, the line integral from there to there changes with respect to Y, because it's a change according to Y. So we're really taking the partial of P with respect to Y dx, and then so it's the change in P for a change in Y, because it's how much we change in P from there to there, and that's a change in Y. So that's why we take the partial of P with respect to Y, because it's how much P changes with respect to a change in Y. And then it's going to be negative because as we go in the positive Y direction, this is negative X. So it's going to be, the change is going to be this way, right? So the change is, for a positive change in Y, we're saying how much negative change in X is there. So it's negative. All right, and then we do the same thing for C2 and C4. So we look at, when we add those two line integrals together, we're doing each one of those a little integral with respect to Y. But then when we subtract them, it's like the change in Q with respect to X, because it's how much different this one is than this one is. And so that's the rate of change with respect to X. Now this one is positive because you have double negative, right? So X is going in the negative direction, and this thing is turning in the negative direction. So you get a double negative, and you get Qx is positive. So really, what this thing, when you do this line integral, it's really calculating the turning rate of change, right? So for this, over this little element, we're getting like a turning rate of change, because we've got how much P changes with respect to Y and how much Q changes with respect to X. And so you put all those together, and your rate of change is like, it's like a curling rate of change. And so we saw that the P of Y has a negative contribution to the curling rate. So the P of Y has a negative contribution to the curling rate, because for a positive change in Y, it's like how much X goes back the other way. But then the QX has a positive contribution, because it's like a double negative. X is going back that way from C2 to C4, and Y is turning down, right? So we're summing all those four together, we get this is the rate of change of the vector field with respect to that little element A, the little area element. And we're going to sum all those up. We're going to sum all those little circulation integral at that rate of change. And that rate of change is like a turning rate of change, right? It's like a turning rate of change. The P's this way and the Q's this way. And so that perspective on it, circulation, summing up all the circulation, gives us that one. And so then that's how those are equal, because they're both summing up the circulation of F around all the little curves. Okay, love to talk more about that. That's, without doing the whole proof, that's just kind of an overview of where this thing comes from. But again, the main thing is that it's the accumulation of lots of little bits of change, and the changes like twisting change, or twisting change in each element, and that ends up being the total change around the boundary when all the sides cancel out, when all the shared sides sum to 0. So then we've got those are equal. Okay, so that's my best 5-minute explanation of that. Any questions? Okay, let's do an example. So we want to evaluate this. So now, using Green's theorem to do examples, it doesn't require learning anything new. It's going to be line integrals and double integrals, which we've already done. But just when you do the double integral, you got to make sure you have the right function. What's the function you want for the double integral? It's going to be q with respect to x minus p with respect to y. Did I get that right? Yeah. Okay, so let's just set up. So we're going to do this both ways. In this example, we're going to verify Green's theorem. How do you verify a theorem? So we're going to verify that this one equals this one. So what does it mean to verify that? And how do we do that? How do we test to see if it's true? Yeah, we got to do both sides, right? We're going to do the line integral according to this loop around the triangle, and then we're going to do the double integral of this. But then rather than doing all the algebra, let's just set up. We'll just set up the line integral and set up the double integral, and then I'll tell you what the numbers amount to for time's sake, because we've done plenty of antiderivatives and plugging in numbers. We can do that, so it's just a matter of setting it up. So why don't you work together for about 5 minutes? We want to set up the line integral, and you're going to set up the double integral. And what's absolutely essential to do this here? Do any of this? Sketch, sketch. So if you have started, that means you've already started a sketch. Okay, 5 minutes to work on your own. Compare what you're doing. Okay, any questions? So my experience in the past teaching this class is sometimes when we get to the final, students have totally forgotten how to do line integrals, how to set them up. So don't be that student. You need to know how to do line integrals, okay? Please ask if I've lost you. And now there's other ways to do it, right? So you could have done, for example, C1, you could have gone t comma 0, t from 0 to 2. And that's the same thing. You get the same thing, right? You could have parameterized this to make this from 0 to 1, so that t equals 0 gives you that point, t equals 1 gives you that point. Okay, so there's more than one way to do it, but just make sure that what you're doing is correct. Any questions about the line integral that I set up? Everyone's following 100%. Don't be afraid to ask. Is that what you got? Something like that. Yes, please. Uh-huh. Yes. Yep. Yeah. You can go from 0 to 1, so that when t equals 0, you get this point, and t equals 1, you get the origin. So what is that? The second one is... So make sure you just check. Just check. Plug in t equals 0, make sure you get the point that you want. Plug in t equals 1, make sure you get the point you want. So what was it again? 2 minus 2t and 4 minus 4t. Is that right? And then in that case, it would be t from 0 to 1. That's a 4. So maybe it's a lot more convenient to do it my way, but if you want to be consistent, always do it using t from 0 to 1 and do the starting point plus the change times t. That's fine. So both of these will give the exact same thing in the end once you do the integral. So those will give you the same integral over C3. Okay, questions on the double integral. So the double integral now is going to be what? Q with respect to x, that's going to be 4, minus p with respect to y is 1 from the vector field, right? And then you can just do easy type 1 here, dy dx. So we'll go from 0 to 2x, and then x goes from 0 to 2. Now let me show you something here. That's just a constant, right? So isn't this the same as 3 times the double integral over dy dx? Agree with that? And when you have a double integral of 1, what does that double integral give you? It's like if your surface was at a height of 1, that value would be the same as area of the region, right? Remember that? So when you do the double integral of 1, you imagine a surface that's z equals 1. So that volume you get is going to be the same as just the area of the region. So we can just do, to actually get this, we just do 3 times what? The area of this triangle, which is 1/2 times base is 2 times. So if we were to work out this double integral or these 3 single integrals and add them together, we ought to get 12. So we actually did that 3 different ways. We did it by area. We could do it by the double integral using antiderivative, and the 0 to 2x, 0 to 2. Or we could work out these 3 single integrals, these line integrals. All 3 ways we should get 12. Any questions on that? Clear as mud? Or a little bit clearer than that? Can we go on? Can I erase? What's that? Oh, well, here I said verify. So in this problem, if I say verify Green's theorem, you got to do both. You got to show that when you do the line integral, you get the same number as. So here you have the choice, right? So here you could do it by antiderivative or use this area approach. So here you have the choice to do the double integral, but then you'd also have to do the single integral, show that 12 equals 12. You get 12 for both. That's if it's verify. That's if it's verify, right? So what about this? Here's a member from your review sheet for exam 3. You guys found the circulation, right? Around the simple closed path shown, up the parabola, cross the line, down the diagonal, back to 0. All right, so I want you to find that circulation line integral now using Green's theorem. Would you be using Green's theorem if you calculated the line integral? You wouldn't be using Green's theorem. So we want to find the value of the line integral, but we want to use Green's theorem to do it. And if we're using Green's theorem to find the value of that line integral, the same one that you did to practice for exam 3, what would using Green's theorem mean? She said setting up the double integral. Make sense? Because Green's theorem says that they're equal, right? So let's check. Let's always check first if f is conservative. Is f conservative? We check what? Q with respect to x versus partial of p with respect to y. Equal? No. So we don't have the trivial case, right? If it's conservative, we know the double integral will be 0, and we know the circulation integral will be 0 because we're in a conservative field. But we don't have that trivial case. So using Green's theorem would mean that this equals what? Double integral over the region enclosed, just d here, of partial of q with respect to x, partial of p with respect to y. That's like our rotational rate of change, right? This is a rate of change function of the vector field. That's like rotational rate of change. We showed that, talked about that earlier. dA. So using Green's theorem means we're going to find this value by doing this. Right? We're going to find that value. That was the value asked for, but we're going to do that instead. And so Qx is 1. Py is 0. All right, so do we want to, now we've got to think, do we want to do type 1 or 2? We could do either. But is there an advantage to one over the other? Is there an advantage to type 1 doing dx first or doing dy first? I want to do dx first. If we do dy first, that would require, we'd have to sum it up because our bottom is different, right? Bottom is different here than it is here. All right, so we're gonna do dx first and then dy, which will allow us to just do one double integral. So this is what, y equals negative x. And we know this is y equals x squared, so x is going to go from negative y to x goes to square root of y. And then from y goes from 0 to 1. And what will this integral in the end compute for us? It'll compute the line integral, but it'll also compute something else. The area of this thing. Now, because we have that parabola though there, we can't just use an area formula like the triangle one we did last time. We actually have to do the antiderivative because this is, who knows what the area of that thing is with a side that's parabolic. Who knows, right? We don't have a simple like circle or rectangle or triangle with this parabolic side. We actually have to go ahead and do the line integral. So let's do it fast. So we're going to have 0 to 1. I think this is going to be what? Radical y minus negative y. Check my math. So that's going to be 2/3 y to the 3/2 plus 1/2 y squared. 0 to 1. 2/3 plus 1/2. So 7/6. 4/6, yeah, 7/6. Does anybody remember doing that problem, calculating the 3 and adding up and getting 7/6? You did? Remember that? Something like that. So when you did it for a review and you added up, you did this actual circulation integral, you added up the 3 pieces. If we've done the math right here, you should have gotten 7/6. And 7/6 ends up being the area of D. Only because, it's only the area of D because this turned out to be 1. If it's something else, if you have a different integram then you could interpret it as difference of volumes or accumulation at that rate. But only if it's a double integral of 1, then does it end up being the area of D. Questions on this example? So now that would be not verifying Green's theorem, but using Green's theorem, right? You're using Green's theorem means you're going to solve the other side, right? If you're using it to find the circulation integral, the boundary, then you're going to calculate the other side and say, by theorem, now 7/6 equals that. So by Green's theorem, this thing equals 7/6. Questions on that? Okay, another example. Here's one. Here's the ellipse x squared plus 3xy plus 4y squared equals 1. So I want to use Green's theorem to evaluate the line integral around that. If the vector field is 5x to the fourth plus y squared 2yx. So I want to know what this line integral is. So here, I'm not saying use Green's theorem, I'm just saying evaluate that any way you can, right? Evaluate that any way you can. So you're going to pick the easier way. Either do it directly, so this would be like directly calculating it, which would what? Involve parameterizing this curve, r equals what? And then calculating the line integral. Or we could use Green's theorem. If all I'm asked to do is evaluate that line integral, and it meets the requirements of Green's theorem, then I have the choice. I could do it directly, or I could find the double integral of this. Excited? Which way you want to do it? You want to do the double integral? Ouch. Slanted ellipse. Read the double integral of slanted ellipse. Anyone notice anything yet? Why is it conservative? Qx is 2y. 2y. Phew. Right? Lesson learned. What do you do first? Always check to see if it's a conservative vector field, right? So what happens? In the double integral, what happens? It's the integral of 0 dA, right? Because you get 2y minus 2y. Other reasoning the other way, we know this is 0. Why? Conservative vector field, we're doing a closed loop around in a conservative vector field. All closed loops in a conservative vector field give us 0 circulation. So both sides 0 equals 0, and this is 0. That's right.
So then why did we get something that wasn't 0 for the cosine t, sine t that we did in the beginning of class?
It's about the vector field, not the parameterization. There's two different things. There's the vector field. That's what you're checking to see if it's conservative or not. And then there's the path through the vector field. Right? So we... the very beginning of class. Oh yeah, we're getting there. We're getting there. Yeah. Okay, questions on this example. So the moral of this one is always check to see if your vector field is conservative to start. If it is, then the answer is 0 for the circulation interval. Okay, so let's talk about regions. So a connected region is 7 minutes. We can do it. Connected region, the idea of it, so the kind of informal definition is it's a region that's connected if it just consists of one piece. And that's all the ones we've been talking about so far. The formal definition then would be, given any 2 points in the region, there exists some path between them that lies entirely in the region. That's the formal definition. So for instance, Connected? No, it's two pieces, right? So there's two pieces to this. And so then you could, because it's not connected, you could find, so if your point A was over here, and your point B was over here, sorry, that probably doesn't show up very well. Kind of. Your point A is B. So then there's no way to draw there's no path that exists from A to B that stays entirely in the region. You have to leave one piece and get to the other. Okay. So that's a connected region means essentially one piece. Okay. A simply connected region means it's connected, so it's one piece, and it has no holes. It has no points missing. Okay, no holes in it. So the formal definition would be every simple closed path that lies in D, inside every single path that lies in D, every point enclosed by that simple closed path is also in D. So, for instance, no matter what closed path you draw that's entirely in D, every point inside that closed path will lie in D. If it's simply connected. But if there's a hole in it, then you could find a path within D such that now inside that path there's points that are not in D. And so what would that path be like? So now if I draw a path around the hole, the missing part, now not every part inside that little C is also in D. So these points are not in D. So that means it's not simply connected, or in other words, there's a hole in it. There's a hole somewhere in your region. Okay, so then what does this mean for Green's theorem? Using Green's theorem with so let's talk through an example like this. So what if so this is radius 1, radius 2, it doesn't matter. So this causes problems with this is a non-simply connected region. So we can get Green's theorem to work if we are kind of strategic in how we do this. We could see this as the same as, we could split it apart into two. So we could have the top and the bottom like this. Now, so if I split it into two parts like that, it's not a good match there. Better. So I just cut it right here. See, I cut it right on the axis right there, and then right there. And now each of those is simply connected. Would you agree? Each of those is simply connected. And so I could go around this one. So it would be C1, then this would be like C2, and then C3, and then C4. And then go around this one. So it would be, say, C5, C6, C7, C8. Oh, what happened? 5, 6, 7. Where I don't know how to count anymore. What? Oh, this is. I thought there was going to be one more. Okay, right. C8. Okay, I was wondering. I thought there was going to be 9, but I already got the bottom. Okay, so what happens now? So to find, say, the double integral over this donut, I could break it apart into these two, and I could do like the line integral around the top simply connected piece, and the line integral around the bottom, and add. And what will happen? Do you see what happens? Yeah, so C4 is going to the right, and C6 is going to the left. So those would cancel out when I added them up. And then C2 is going to the right, and C8 is going to the left. And when I add this all up, they're going to cancel out. So what are we going to be left with? Well, okay, so how? It's C1, C1 plus C5 will be the outer boundary, but then plus C3 plus C4. But notice that they're not opposite. Why aren't they opposite? Because as you walk on those, as you walk on those, even though it looks clockwise, as you walk on it, the region's to the left. You see that? On C3, and when you walk on C4, the region's to the left. So we're still going to add them. So really what happens is we can apply Green's theorem as long as we consider both rings all the boundary. So we're going to keeping the region on the left. So we're going to, for the line integral, we're going to go around this loop counterclockwise, keeping the region on the left, but then we go around the inner loop clockwise. If we add those two together, then we can still apply Green's theorem, thinking of those two, this and this totally as the boundary. So then I will leave you to think about, we don't have time to return to the first. We'll have to keep shelving that for 2 days, but that gives you a chance to think about it and see if you can figure out what was going on in that first example. Oh, so there's a written homework on the stuff before Green's theorem. The written homework is due Thursday. Hopefully you started that. So recitation will be actually working Green's theorem examples today, okay?